Hello and welcome to Fundamentals of Radar. It depends on the application, a tutorial introduction with Dr. Brian Sekira. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Techniques Society webcast, which is sponsored by Rohde & Schwartz. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the Live Slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides and additional resources to be presented today. Now let's introduce our speaker. Dr. Brian Sekira is a principal professional staff member at Johns Hopkins University Applied Physics Laboratory. He's been there since 2001. During this period, he has assisted with the development of deep space communication subsystems aboard the Messenger spacecraft that orbited Mercury, stereo spacecraft pair that orbits Earth, and New Horizons spacecraft that flew by Pluto. He worked with synthetic aperture radar imagers that flew on the lunar orbiting Chandrayaan-1 and Lunar Reconnaissance Orbiter LRO missions. He previously worked at Geophone, where he architected very small aperture terminals, and at Martin Marietta, where among other programs, he served as technical director on a program for a missile radar on a high-speed interceptor. Dr. Sekira is adjunct faculty of Johns Hopkins University, where he teaches a graduate-level course on electromagnetic transmission systems and antenna systems. Dr. Sekira is a senior member of the IEEE and in 2001 served as the program planning chair of the International Microwave Symposium held in Baltimore. He's past chairman of the Baltimore section and of the Baltimore chapter of the IEEE Societies for Microwave Theory and Techniques and Antennas and in Propagation, and also served on the IEEE Standards Commission. He's a member of the Education Subcommittee within IEEE MTT's ADCOM and has published 42 papers and holds 9 patents. So now it's my pleasure to turn the virtual podium over to Dr. Brian Sekira for Fundamentals of Radar. It depends on the application, a tutorial introduction. Brian?
Thank you, Mike, and hello, everyone. My name is Brian Sekira, and I add my welcome to all of you to this first in a series of tutorials. By the Education Committee of the Microwave Theory and Techniques Society of IEEE. This tutorial is on the fundamentals of radar. At the outset, I must direct you to the many excellent and recent texts that are available on the subject. One of those texts is Airborne Radar by George Simpson. There's also an excellent set of YouTube presentations and downloadable PDF files on radar by Bob O'Donnell under the auspices of MIT's Lincoln Laboratories, and I encourage the interested listener to access this material. It is not my intent to duplicate those excellent expositions. Rather, I will focus my presentation on the statement, it depends on the application. You may have heard such a response in many predecessor discussions where the presenter was asked a question that did not have a different pat answer. Nevertheless, such questions merit detailed response because they uncover constraints and relationships among factors that affect system and especially radar performance. The purpose of this tutorial is to explore the nature of those relationships to application and to expose the coupling between variables that determine radar performance in these applications. To do this, I will develop the radar formalism differently from any that you might have experienced from previous contact with the subject. Specifically, I will developed the formalism in a manner that allows us to answer the question, what can be said about a radar system without reference to its end application? How does the end application and its implementation affect the radar system? The word radar is an acronym for radio detection and ranging. Its function is to broadcast a signal and listen for echoes of that signal. Encapsulated in this simple statement is a notion that a radar must distinguish echoes from other interfering signals in ever-present noise, and, having confirmed the receipt of an echo, the radar must measure the time lapse between transmission of the signal and its receipt, as the animation illustrates. The conversion from measured time lapse to distance is accomplished by utilizing the universal speed of propagation of all electromagnetic signals. Although sophisticated enhancements permit radars to measure the kinematical state of the source of an echo, we shall for the time being adhere to the original premise of radar as a system that detects an echo and measures the distance to its source. Although there are many ways to classify radars, the classification that is germane to this tutorial is that of monostatic and multistatic radars. We adopt the definition that a radar is monostatic if it transmits and receives signals from a common antenna aperture. Usually, the transmitted signal is many orders of magnitude greater than any received echo, and therefore it is not feasible to conduct full duplex radar operations, that is, transmit and receive simultaneously with a single aperture. Fortunately, the time lapse between transmission and echo arrival enables time sharing of the aperture between these two functions by interleaving transmission and reception. That said, there are short-distance applications, notably toll barrier radar, where the received echo is strong enough relative to the transmitted signal that cancellation techniques render it feasible to use a single aperture for simultaneous transmission and reception. But such opportunities for monostatic full duplex implementation are rare. Multistatic radars have separate antennas for transmission and reception. In this case, antenna separation is often sufficient that full duplex operation is possible and may in fact be critical for prosecution of the radar's primary functions. Of these, the bistatic radar is an important special case in its own right, and because many of the relationships developed for the bistatic case reduce to the monostatic case in the limit when the two antennas coincide. Irrespective of type, a radar must do work, that is, expend energy to fulfill its primary functions of detection and ranging. First, the radar must illuminate the target or scene with electromagnetic energy and capture echoes that are returned from the scene and our target. A significant amount of work done by the radar is manifested as energy expended in computation for detection and characterization of targets. Computation involves estimation of noise, setting of thresholds, and cataloging signals that cross such thresholds. Not all threshold crossings are echoes, and so additional computation must be performed to determine the pedigree of signals and so distinguish between interfering signals and echoes. This aspect of the computation is of increasing import in modern radars that operate in dense signal environments and in which spectrum is likely to be shared by a number of co-primary users, such as automotive radar-equipped self-driving cars that travel along a common highway. Among the threshold crossings that have the same pedigree, the radar may do additional computation, for example, to distinguish targets from clutter and multipath. Part of those calculations involve computation of directions of arrival to distinguish ghost targets from real ones and determine range, range rate, radial acceleration. In short, the kinematic state of the target or targets along the radar's line of sight. Depending on the platform, computation operations may involve formatting so that the data is conveniently displayed or else sent by telemetry links to a data center for further processing. This brings me to the first difference in my exposition from those of previous presentations on the subject. In deference to the previous chart that speaks to the work done or expended energy, I will develop a formalism in terms of energy instead of power, as nearly all other introductions are wont to do. This has the advantage of advancing development of concepts while preserving agnosticism to application. It also offers natural insights into radar performance, as we shall soon see. The radar equation,
Brian?
yes?
Sorry, will you be sure to advance the slides?
I am on bistatic radar equation 1 of 3.
Yes, can you please make sure I've been advancing the slides. Will you advance them as you go, please? Thank you.
Yeah, I am trying to, but I think, well, one of the keys is working, but the other is not. So I'll try and see.
Okay. Yeah, just use the yellow triangle there in the live view window.
No, there's no yellow triangle showing up on my window.
Oh, okay, you may have to just refresh real quick.
Okay.
Sorry for the technical difficulties here. Are you able to advance the slides?
Okay, yes, I now have it. Thanks.
Great. Okay, thank you.
Okay.
Thank you.
So, the radar equation addresses only one component of the total expended energy, namely the energy to illuminate the target, which we denote by E sub Tx as represented by the box in the lower left corner of the screen. Part of the energy is lost in the plumbing that connects E sub Tx to the antenna. Thus, the energy delivered to the antenna is E sub Tx divided by L sub Tx. If an antenna was not present, the energy would spread isotropically over a sphere of radius R sub Tx, which is the distance to the target. The transmitted energy density at the target's distance is the energy delivered to the antenna divided by 4 pi R sub Tx squared. The antenna concentrates energy in the direction of the target and in so doing boosts the energy density over isotropic dispersal by its gain, G sub Tx, which is related to its aperture area A sub Tx, efficiency N sub Tx, and the wavelength as indicated in the graphic. However, as the graphic shows, the energy is not concentrated at the bore site, but has an angular distribution that is defined by the antenna pattern. Although the antenna pattern has a main lobe of finite width about the peak and auxiliary lobes, known as side lobes, in other directions. For the antenna pattern shown here, the gain of the auxiliary lobes is 1% or less than that of the main lobe, because each of the faint concentric circles represents 20 dB reduction in gain in this polar representation. Nevertheless, the integrated energy over all the side lobes does not illuminate the target and therefore represents a loss. There is another antenna pattern-related loss owing to the fact that the line of sight to the target does not coincide with the antenna's bore site, and therefore the gain along the LOS, the line of sight, is not its peak gain. This is known as pointing loss. There is further a path-related loss due to weather as depicted by the thundercloud in this graphic. For space-based radars or targets, the ionosphere contributes yet another loss. Together, we account for these losses and lump them in a single term called the channel loss of the transmit path, L sub ch underscore tx. For this transmitted energy density in joules per square meter is given by the formula at the top left-hand side of the slide. It is evident from this next graphic that the target intercepts but a small fraction of the transmitter's energy, and only a small fraction of the intercepted energy is directed towards the receiver's antenna. We represent this effect by a bistatic scattering cross-section, sigma, in square meters. Thus, the energy scattered in the direction of the receiver is the transmitted energy density multiplied by sigma. Much like the transmitted energy, the scattered energy per unit solid angle must be conserved, and so the energy density weakens as the square of the distance between the target and the receiver. That is, the energy density at the receiving antenna is the transmitted energy density multiplied by sigma divided by 4 pi r sub rx squared. In addition, there are losses due to pointing, pattern, and weather that are lumped into the channel loss on the received path, L sub ch underscore rx. The energy intercepted by the receiver antenna is proportional to its effective aperture, which is the product of its physical area, A sub rx, times its efficiency, eta sub rx. The energy intercepted by the receive antenna suffers loss due to receive plumbing, and so the received energy is as given on the lower right-hand side of the slide. We may recast the radar equation in the manner shown above, in which the right-hand side is the transmitted energy multiplied by a number of factors that are all dimensionless. So the dimensional balance of this equation is obvious. In particular, note the replacement of the target cross-section sigma by the dimensionless term g sub sigma. We will have more to say about this later in the discussion. Also note the straightforward manner in which we recover the case for the monostatic radar from the bistatic case. In most other treatments, it is usual to designate all losses under a single variable L. But the listener should be alert to the fact that L contains a varied source of system losses, only some of which are mentioned explicitly in this development. We will encounter a few others as this tutorial progresses. The first observation that we make is that the natural unit of length for radars is its wavelength. For example, the received energy is inversely proportional to the fourth power of the range measured in wavelengths. In the case of a bistatic radar, the effective range is the geometrical mean of the transmitter and receiver distances to the target. The gain of the antenna is proportional to its aperture area measured in squared wavelengths. Analogously, the scattered energy from a target is proportional to its cross-section measured in square wavelengths. Some contribution to losses have dependence on path length measured in wavelengths, and the Doppler shift in frequency is directly proportional to the target's range rate, expressed as the number of wavelengths per second. It is interesting to note that if one took an existing radar and merely operated it at higher frequency or shorter wavelength, the gain of the antenna would increase, but so would the spreading loss by the same factor. So there's no apparent benefit to operating a given radar at a higher frequency than for which it was designed. In fact, performance would actually diminish because of higher losses due to other factors such as pointing and weather, as well as tolerances on surface shapes and placement of feed optics to retain the same illumination as at the previously longer wavelengths. An antenna of a specified shape has a pattern associated with its size and shape, and that pattern varies with viewing aspect to the antenna. Like an antenna, any other object has associated with its shape a scattering pattern and a quote gain unquote that is denoted by G sub sigma, which is directly accessible to measurement as is with an antenna. So we use G sub sigma to unify the concepts of scattering to antenna and target alike. In this era of big data and high computational power, simulation with measured scattering patterns offers superior insight into radar performance. Specifically, the measured pattern of G sigma reveals peaks and nulls in the scattered energy, much as they do in an antenna pattern measurement. Second, G sub sigma alerts the radar analyst to the relationship between target size and wavelength, especially for targets of small size. The graphic of the scattering behavior of a metal sphere illustrates the point. The scattering cross-section of the sphere equals its geometrical cross-section only when the sphere's circumference is about 20 times its wavelength, or its geometrical cross-section is 32 times lambda squared or larger. As the size of the sphere gets smaller, its scattering cross-section departs significantly from its geometrical cross-section as shown. Third, analytical extension to multistatic cases is readily facilitated through measured G sub sigma, which incorporates the dependence of the scatter on pointing aspect angles theta and phi of both transmitting and receiving antennas and their associated polarizations. Unlike the monostatic pattern shown in this slide, bistatic G sub sigma profiles facilitate assessment of specular and non-specular interference between multiple radars, as with radars on multiple automobiles traveling along a multi-lane highway. For reasons that will be clear very shortly, it is convenient to express the radar equations in terms of signal-to-noise ratio, or SNR, which is the ratio of the received signal energy to noise energy E sub n. Our motivation for doing this is because SNR drives two probabilistic attributes of detection, namely the probability of false alarm and the probability of detection, which we will examine next. We mentioned previously that to perform detection and ranging, a radar system must distinguish between energies of different pedigrees. We will examine on a continual basis the various attributes of a signal that establishes the pedigree of its associated energy. Propagating radar signals are vector field distributions that are endowed with amplitude, phase, frequency, direction, and polarization. However, once lodged inside a receiver, the signal is a scalar voltage or current having two real attributes, amplitude and phase. The two properties arise from the carrier or center frequency and modulation of the signal and may be conveniently expressed as an ordered pair of real numbers. In other words, a signal in the receiver may be represented by a single complex number composed of two real numbers that are commonly referred to as real and imaginary pairs. At the sending or transmitting end, the signal's amplitude, frequency, or phase may be varied to impress information on its carrier. The propagation distance introduces changes in signal amplitude due to attenuation and changes in phase owing to the length of the path being many wavelengths long. Weather could introduce amplitude and phase modulation as could the target, but we will ignore these incidental modulation effects for now and return to them later. In the domain where signals are complex, it's evident that noise should affect both parts of the signal. It is also evident that noise should affect real and imaginary parts of the signal equally. We therefore represent noise as two random sequences, one for the real part and the other for the imaginary part. There is no reason to believe that the two random sequences have any relationship to each other. We therefore consider that the two are independent. We invoke the central limit theorem that states that any random sequence tends to a Gaussian distribution in the limit that the sequence is indefinitely long. Further, because positive and negative amplitude fluctuations are equally likely, we anticipate that the mean value of both Gaussian distributions is 0. Also, we anticipate that their variances are identical because noise affects both parts of the signal equally. We therefore represent their probability density distributions, or PDF, by zero mean Gaussians with identical variance v sub n squared. One representation of the PDF by Gaussians implies that we have a large enough number of independent voltage samples to mimic a Gaussian distribution and to establish statistically meaningful quantities such as mean and variance. This implies that we observe the noise voltages over an interval of time large enough to collect a statistically significant number of samples. The variance of these samples multiplied by the time over which it's collected is proportional to the noise energy accumulated in the receiver. The statistical independence of the real and imaginary distributions means that the PDF of any real imaginary pair is a product of the separate distributions. We convert the probability density functions from rectangular to polar format and see that the transformed probability density is expressed as a product of separate densities for magnitude b squared and phi, thus indicating the statistical independence of the magnitude and phase distributions. The distribution for magnitude v squared is exponential, whereas the distribution for phi is uniform. First, we interpret 2 v sub n squared as the sum of the variances of the real and imaginary parts of a noise voltage fluctuation and represent this as the variance of the magnitude of the complex noise voltage, magnitude v sub n. Second, the transformation of the bivariate distribution in terms of the probability of the squared magnitude of the noise voltage fluctuations suggests a relationship to noise power, which, when sampled over time, relates to noise energy. In terms of normalized energy, the PDF is a simple exponential. The probability of false alarm, P sub FA, with respect to a given threshold is the probability that a fluctuation of noise voltage will exceed that threshold. For the PDF just derived, PFA equals the exponential of the negative of the normalized energy threshold. We solve for the normalized threshold as the natural logarithm of the reciprocal of P sub FA. That ratio is approximately 14 for P sub FA equals 10 to the minus 6, or 1 part in a million. Often, the probability of false alarm may be expressed as false alarm time or false alarm rate. If given a false alarm time, calculate the number of threshold crossings in that time. The reciprocal of that number is the probability of false alarm. If given a false alarm rate, calculate the threshold crossing rate in the same unit of time as specified in the false alarm rate. The ratio of the false alarm rate to the threshold crossing rate is the probability of false alarm. Now let us compare the probability densities in the absence and in the presence of a signal. We plot the probability density of the noise-only energy in red and the corresponding probability density in the presence of a signal with energy E sub Rx in blue. Note that the probability density of the red curve is normalized to unity and that the integral of the density over all energies, which is the area under the red curve, is unity. We expect that the noise distribution in the presence of a signal will have its mean shifted to the signal energy. These features are shown in the plot of the blue curve. The probability that a signal will be detected is the area under the blue curve for energies that are greater than the threshold. It is straightforward, see the posted handout, to compute the probability of detection P sub d for the given probability density of the noise distribution in the presence of a signal as shown above. As one might expect, the SNR depends on the probability of detection and probability of false alarm. For P sub d equals 0.9 and P sub fa equals 10 to the minus 6, the required SNR is approximately 21 or 13.2 dB. It is interesting to note that the detection criteria is satisfied solely by energy ratios. Apart from the assumption that the noise distribution is Gaussian, nothing is yet known about the signal or noise individually. This indicates that a rich variety of signal pedigrees can accomplish detection performance as long as its energy and accompanying threshold satisfy prescribed ratios to noise energy. In typical environments, there are additional non-Gaussian sources against which a practical radar must contend. These sources arise from natural causes, like electrical storms and solar activity, and artificial origins, for example, an interference from broadcasts of various forms, ignition noise from automobiles, etc. And their effect is to increase false alarms. Preservation of detection performance in the presence of these noise sources requires elevated thresholds and commensurately higher SNR. In the first slide, we showed an animation of a transmitted signal impinging on a target and its echo arriving at the radar's receiver. In a perfect receiver, the reception gate would open precisely at the time of arrival of the echo, and the receiver would sample the signal for only the duration of each echo. In that scenario, every sample would contain echo energy and noise energy. However, this level of perfection threatens the very existence of a radar because if the target's spatial and kinematic attributes are already known that precisely, then there is no need for a radar to measure what is already known. In practice, there is some uncertainty in the time of arrival of the echo, and hence the reception gate must open somewhat earlier than the arrival of an echo to account for that uncertainty. Also, for an extended target, the leading edge of the target arrives at the receiver earlier than the trailing edge, with times of arrival everywhere in between for those portions of the target that are within these time boundaries. These temporal profiles, in turn, depend on the look aspect of the target. Because the target and its look aspect are unknown a priori, sampling of the signal must necessarily extend beyond the echo's termination. As a result, noise energy is sampled for a somewhat longer duration than echo energy. Suppose the transmitted signal is a pulse carrier whose frequency is constant. The spectrum of that signal is a sin x over x, or sinc function, centered at the carrier frequency of the carrier. An ideal filter would mimic the spectrum of that signal by providing gain in proportion to the spectral lobes of the sinc function and having zero gain at the signal's nulls. In this way, the filter rejects noise where the echo level is low or zero. In practice, uncertainty in target kinematics precludes such exquisite spectral matching. Doppler uncertainty produces a residual shift in the center frequency of the spectrum. Uncertainty in radial acceleration smears the Doppler. And changing aspect to the target produces a time-varying scatter signal with modulation which generates sidebands that are not predictable. Energy in the sidebands manifests as a signal loss known as target fluctuation loss. Weather can similarly cause fluctuation loss. We shall have more to say about these fluctuations later in this development. For the time being, it is sufficient to note that a mismatched receiver will have nulls displaced from that of the signal, and therefore sample noise and suppress echo energy because of that displacement. The SNR is thus impaired. Given that the receiver accumulates noise energy over a longer duration than echo energy, it is legitimate to ask if the accumulation of echo energy can ever outpace that of noise energy to establish the SNR that is compatible with detection performance. To answer this question, we must come to grips with the pedigree of a signal. What is pedigree anyway? It is a set of characteristics that distinguishes one stimulus from another. What characteristic could permit accumulation of E sub Rx to outpace that of E sub n? One answer to that question is periodicity in conjunction with stroboscopic sampling and accumulation, as depicted in this slide. A periodic voltage is conveniently represented in the complex plane as a phasor that rotates about the origin. The time in which the phasor completes one rotation is the period of the signal. If this voltage is sampled every period or integer multiples thereof, samples of the phasor appear stationary, much the same way by which a rotating object appears stationary under a strobe light. Because the relative phase difference between each sample is zero, accumulating these samples amounts to simple arithmetic addition of their amplitudes. Thus, if the amplitude of the phasor is magnitude V sub Rx, the accumulated amplitude after m samples is m sub magnitude V sub Rx, and the associated energy accumulated is proportional to m squared times the magnitude of V sub Rx squared. In other words, for a periodic sample stroboscopically, energy accumulated grows as a square of the number of samples accumulated. With random noise, there is no correlation between samples, and therefore the total noise energy just grows as the number of accumulated samples times their average. Hence, the SNR for the stroboscopically sampled periodic signal grows as the number of samples accumulated. So if SNR is 1 per sample, SNR is equal to m after m samples. So to attain SNR equals to 21, for PD equals 0.9 and P sub FA equals 10 to the minus 6, 21 stroboscopic samples need to be accumulated. But suppose that noise is sampled over a 30% longer duration than the signal. Then the required SNR would be achieved after 28 samples. Inherent in this description is the time taken to accumulate sufficient energy. It is aptly called the integration time. Stroboscopic sampling is known by the term coherent sampling, and the time interval over which it extends is known as coherent integration time or coherent processing interval. Another way of sampling signals is non-coherently, in which the SNR grows as a square root of the number of samples accumulated. This is a less efficient way of accumulating energy, but is unavoidable in certain circumstances. An important point to note is that the foregoing considerations establish lower bounds on the detection time, irrespective of application. That is, detection time should be long enough to accumulate a statistically significant number of samples and to integrate sufficient signal energy to obtain SNR to meet the specified probability of detection and probability of false alarm. Further to our discussion on lower bound on detection time, the question arises as to whether there is a fundamental upper bound on integration time. The answer to that question depends upon how the radar is modeled. If the radar is modeled as a linear time invariant system, LTI, then as we have seen, fluctuations in target scatter and weather negate LTI assumptions. Why? In a linear system, the amplitudes of all spectral components of the input signal must be scaled by the same factor. Their phases must be altered in linear proportion to their frequencies, and no spectral components should appear at the output that are not present at the input. As we have seen, fluctuations in target scatter and attenuation and phase fluctuations caused by weather introduce sidebands, that is, spectral components that are not present in the input signal. If detection duration is sufficiently shorter than time variation of the fluctuations so that fluctuations can be ignored, then the radar can be adequately represented by an LTI model over that duration. The detection interval is thus upper bounded by this assumption. If the radar is modeled as a time-varying system, the upper bound is no longer limited by fluctuations owing to weather and target. In this case, system analysis is limited by the fidelity of the model. We recognize from the slide titled Signal-to-Noise Ratio that for an LTI system, all of the time-varying factors reside in the SNR and in E sub tx divided by E sub n. Extension of this to a case where some of the factors that multiply E sub tx over E sub n are time-varying may be implemented by expressing each of them as a sum of a time-invariant component and a time-varying component as shown. We then absorb all of the time-varying portions into a modified SNR that we call SNR prime. Then SNR prime equals the product of a time-invariant factor with E sub tx divided by E sub n. We can extend the validity of an LTI model if we assume that the time variation of these quantities is noise-like and can be handled statistically. This is the basis for swirling models for target fluctuation. In general, the statistics for these random variations follow a distribution that is different from Gaussian. The interested listener is encouraged to consult www.radartutorial.eu for further description of swirling models. Of course, further information may be obtained by consulting papers by Markham and Swirling. Within the context of target fluctuations, we point out that bistatic scatter fluctuations of a right circular cylinder are reportedly less than monostatic fluctuations and diminish with increasing bistatic angle. Furthermore, for a given target, bistatic scatter is stronger than monostatic scatter. These findings could present strong and persistent interference problems for automotive radar. Thus far, our analysis has focused on energy ratios. We now turn our attention to the individual energies that comprise that ratio. In this slide, we address system noise temperature. We previously argued that electrical signals have 2 degrees of freedom, represented either by magnitude and phase or by real and imaginary part. The equipartition theorem of statistical physics states that the energy of any system in thermal equilibrium at temperature T sub cis is equally distributed among its degrees of freedom and equals half K sub B T sub cis per degree of freedom, where K sub B is Boltzmann's constant. For an ideal receiver, meaning the one that has no temporal and or spectral mismatch, the noise energy is K sub B T sub cis. For a practical system, E sub n is equal to L sub mis K sub B T sub cis, where L sub mis is a mismatch factor that accounts for the non-ideal behavior discussed previously. For well-designed radar systems, L sub mis lies between 1.1 and 1.6. It is clear that calculation of system noise energy rests on the estimation of system noise temperature, and it is here that we encounter a narrowing of the generality of our treatment. It is important to reference noise to the same point in the system as a signal. In our development, we have referenced a signal at the input of the receiver, and we do likewise to the noise. Noise emanates from a variety of sources, and from the viewpoint of a radar system, it is convenient to categorize these as arising from the scene viewed by the radar's receiving antenna, the plumbing from antenna to receiver, and the receiver itself. Scene temperature is perhaps most strongly application dependent. Low-frequency radars for foliage and ground penetration must contend with galactic noise, which is stronger than black-body thermal noise in the sub-UHF region where these radars operate. This is shown in the diagram at the upper right hand of the slide. In addition, water vapor and oxygen absorption frequencies limit use at those frequencies in terrestrial radar applications. Weather causes variations in sky noise that increases at high frequencies. Rain increases attenuation that increases at higher frequencies, as shown in the lower right of the slide. This attenuation also introduces noise. Scene temperature is a sum of contributions from all sources weighted by the receive antenna pattern. Clearly, this quantity depends on whether the platform is at a site on Earth's surface or is airborne or in space. In each of these cases, the orientation of the antenna determines the scene temperature depending on whether the surface of the Earth is in the antenna side lobes, as with the terrestrial radar looking upwards, or whether or not the sun is in the antenna side lobes or in the main lobe. Else, Earth's surface may be in the main lobe, as with an airborne radar looking down at it. Or in the case of a spacecraft orbiting around one of Jupiter's moons, noise arises from high radio emission from the giant planet itself. Quite clearly, the application determines which of these sources of noise is important and what constraints their presence imposes on performance and operation of the radar. Besides scene, contributions to noise arise from the antenna, plumbing between the antenna and the receiver itself. Antenna temperature is related to its physical temperature and its efficiency as indicated. The temperature of the plumbing and its loss contributes to the noise. A similar equation relates weather loss and its contribution to noise temperature. The receiver generates excess noise that is related to its noise factor, measured at some reference temperature, commonly 290 K. The calculation of system temperature depends on its location in the system. The calculation represented by the equation above is reference to the receiver input as shown. The scene and antenna temperatures are attenuated by the plumbing loss, and the plumbing and receiver add their own contributions. All of these contributions combine to give a system temperature and hence noise energy at the receiver input. The receiver must accumulate sufficient signal energy within the permitted detection time to satisfy probability of detection and probability of false alarm for a specified target size at a given maximum range. To do this, the transmitter must direct sufficient energy at the target within that time, or in other words, transmit power at the target. We consider an example in the following slide. An airport surveillance radar, ASR, operates monostatically in the frequency band between 2.7 and 2.9 gigahertz to afford all-weather coverage. A mechanically rotating antenna provides full azimuth coverage. Because the radar must keep track of targets, it conforms to a specified revisit time, which determines the rotation rate of the antenna, typically 15 RPM. The radar must resolve targets approaching, receding from different directions, and for that purpose meets a specified angular resolution of typically 1.5 degrees. So the antenna beam illuminates a given direction for 1/60th of a second, which is the time available for detection. Here we see how application couples or constrains radar variables. Because the antenna must be pointed to the target to intercept its arriving echoes, the round-trip time for echoes must be smaller than the detection time. Thus, the application constrains the maximum range of such a radar. For an ASR-11 radar, the maximum round-trip time is 1/1500th of a second. This is equivalent to a maximum range of 100 kilometers. Also, because the antenna beam has a shape that reduces its gain by 1/2 at beam edges, the two-way gain reduction is 1/4. So as the antenna sweeps across the target, the echo energy starts out at 1/4 of its peak strength, rises to peak strength, and then diminishes to 1/4 of its peak strength. This variation provides less illumination than a uniform beam would, and hence results in a scan loss. So in addition to constraining the range, the setting of detection time couples to system losses as well. This coupling among radar variables is universal among all radars. Only the variables involved and the nature of their interlocking constraints varies from application to application. table provides an example of the link analysis that is used using the energy formalism developed in this tutorial. As you see, a number of factors have been put in there. For example, the antenna's gain, the two-way gain is 68 dBi, the spreading loss at maximum range for a wavelength of 10.7 centimeters at 2.8 gigahertz is 282.8 dB. And in fact, when you take into account all of the sum of all of those factors, it comes out to 196.2 dB. In order to detect a small target at a maximum range of with 90% probability of detection and 1 in a million probability of false alarm, we need an SNR of 13.2 dB as a receiver. So the transmitted energy to receive energy is 209.4 dB. So the transmitter must exceed the noise energy at the transmitter end by that large number. The system noise temperature is dominated by the seeing condition where the line of sight to the target is very close to the line of sight to the sun. So T sub 6 is 2000 Kelvin. We include a temporal and spectral mismatch factor of 1.5 to estimate the receiver's noise energy at minus 194 dB joules. Then the transmitted energy is about 35 joules, and this is equivalent, and it must be expended in 1/60th of a second. So this is equivalent to an average power of 2.13 kilowatts. The FAA website notes that the average power of an ASR-11 is 2.1 kilowatts. Similarly, because the minimum range of operation of this radar is 12 kilometers, it means that the pulse width cannot exceed 80 microseconds. And also, you must wait for the time of arrival of a target from 100 kilometers before you send the next transmitted pulse. And so that sets a limit on the duty factor of 8.4%. And so the peak power that is needed is 25.32 kilowatts. The FAA website quotes the peak power for the ASR-11 as 25 kilowatts. This example serves to illustrate application-induced coupling of radar variables such as coverage, revisit time, and angular resolution have coupled detection time, range, and losses. It further demonstrates that the formalism developed from energy considerations leads to accurate prediction of the transmitted RF power required to accomplish detection. Target kinematics can be a determining factor in constraining the available integration time. While it is not the case in this example of the ASR radar, it could be an example. For example, if we had, instead of a range resolution of 150 meters, if we had a range resolution of 1 meter, then the uncompensated range rate would be like Mach 0.18, which is well within the span of range rates encountered in aviation. And similar considerations apply to the case of radial acceleration as well. For example, in this case, radial acceleration is not of concern because it would have to be very, very high compared to what is normally encountered. But if you were considering a 77 gigahertz automotive radar operating with a detection time of 1/60th of a second, the uncompensated radial acceleration cannot exceed 0.72 g. In this discussion, I've been careful to use the word uncompensated to signify the unknown portion of a kinematic quantity. In tracking situations where there is some knowledge of this quantity, this knowledge can be used to compensate for that quantity. The uncompensated portion is then the error in this knowledge. So we have examined a radar formalism that emphasizes the work done to detect targets. This leads us to the concept of energy expended to accomplish the function of detection, which acquires the sub-functions of target illumination, echo reception, and computation. Of these, we've examined only the role of illumination in detection and see that for a Gaussian noise, knowledge of energy ratios is sufficient for realizing a given detection criteria specified by P sub FA and P sub D. There are overarching temporal constraints over which the energy can be accumulated during reception. These constraints are dependent on the model used to describe the radar system and on the assumptions underlying that model. We also explored deviations of a practical radar from that of an ideal match receiver. Next, we saw how estimation of noise energy and available detection time were application-driven and how they constrained other radar variables. The detection time constrains the temporal interval over which illumination energy must be expended and thus determines the RF power of the transmitter. Although our treatment did not use bandwidth explicitly, it did address spectral implications as discussed. Another aspect of our radar formulation is to identify wavelength as a natural unit of length for all radars and therefore express all quantities in terms of wavelength. This unifies the concept of scattering for antennas and for targets and reinforces the intimate relationship of target dimensions and wavelength and its scattering properties. Just as an antenna has a pattern and a gain 4 pi times the effective area divided by lambda squared, so also a target has a scattering pattern and a coefficient 4 pi effective target area, or RCS, divided by lambda squared. This concept is particularly amenable to extension to multistatic circumstances and is compatible with big data analytics. Furthermore, expression in terms of wavelength leads to straightforward revelation of frequency scaling and dimensional checking. We have examined only the energy expended on target illumination. What about other energy expenditures? To understand this, we must look at more complicated case of detecting multiple targets, which requires the radar to properly associate each detection with each target and have sufficient dynamic range to detect small targets in the presence of large ones. Discussion of this topic in Airborne Radar by George Simpson and in the University of New Hampshire, or UNH version of Bob O'Donnell's online video course provides excellent information on the subject. In addition, we must examine detection in interference environments. Clutter is one of those interferers, and the listener may obtain information from Simpson's book and from MIT Lincoln Labs and UNH versions of Bob O'Donnell's online video course. These references describe the computation necessary for mitigation of clutter. Dense spectral usage, for example, when multiple automotive radars emit signals, is another source of interference, and the listener is referred to a distinguished microwave lecture given by Dr. Marcus Gardel on this subject. This talk focuses on computation that automotive radars must perform to mitigate that interference. All this will give you, the listener, a comprehensive look at the energy expenditure that must be incurred for detection and ranging. Then you would proceed to the further study about tracking and imaging. Thank you for listening.
Great. Thank you very much, Brian. Folks, I'm afraid we are actually out of time here. We do have a number of questions in the queue that you submitted. Thanks for submitting those, but we're not going to have time to get to those. But the presenter will follow up with these questions offline. Also, as we said earlier, this session will be archived on the Society website at mtt.org. All registrants will get an email reminder with a website address when that is available. For attendees who would like to receive PDH credits, please follow the link in the webcast view and use the code provided on the last slide of this presentation. Once again, I'd like to thank Rodian Schwartz for our sponsor of this webinar, and also Dr. Sikira for this excellent and informative presentation. Special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you and have a great day.